All right, guys, any questions from there? Yeah? Yeah, so on the calculator you mean, or you mean? In the calculator?
Way too long with the numbers that I have. Like, yeah, no.
Anything else while that's warming up?
For the pop that? Yes. Yeah, I didn't need the other.
Okay. So guys, if you wanted to do like
I didn't need to.
I don't know, 102, choose 12.15 to the 12.85 to the 90. If you wanted to do that, nobody had this one, but everybody had something sort of like that. All right. You guys with me? If you want to plug that in the calculator. Now, in the book, we use this in place of the whole factorial business. So in the book, they've got this big formula with the factorials in it. But I just go ahead and use this in the calculator. There's nothing to really be gained by this conceptually. So I just have the calculator count how long our list would be. So in the calculator, you would do 102. Yeah. Probability, choose, let's say, 12 times 0.15 to the 12 times 0.85 to the 90. So that'd be like an 8% chance or something, right?
You have the variance. What does the formula look like again? Sorry, you write the formula.
Yeah. Everybody's cool with that one, right? That was the NCX, P to the X, Q to the rest formula. You mean for the sum of X, the variance like this here?
Yeah. Wait, that was so much different than what I've seen during the book, and that's what got me.
The book gives you several, right?
Yeah.
And this is the best one to use.
Okay.
Yeah. And if you'll remember, I spared you the summation algebra steps. I spared you that. If you feel gypped, if you feel like you're missing out, you could always come see me and I can show you the steps how to get there. But the actual formula started off like this, where you can see this looks like what we're used to, right? And on the bottom of P is N, so that looks exactly like the old formula for standard deviation, right? But this calculation-wise, there's way too many steps. This is a much quicker one to use, right? If you want to, you can put this on a flow sheet and use it, but again, and we foiled this out. We did like the first couple steps, and we saw where that come from, and then I just said, I'm not going to show you, because that would take a whole semester to go through summation algebra. Not a whole semester, but anyway. To show you where that comes from, but at least I showed you where that came from. Yeah. Because when you have this, then you just need X, P of X. What's your next one?
XP of X.
XP of X, and that's of course where your mean comes from, and then your next one be,
X squared P of X.
which is the piece that it needs here.
Yeah.
So unfortunately, a lot of people, they very often will get this number, and they'll say that's the variance or something, and that's not true. That's part of the variance, right? You got to subtract the square of the mean from it. It's just a part of the formula. Okay. Yeah.
So because it would be like 7 point blah 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 to the exponent or something that's wrong.
If your variance, if your...
Or like for that.
Oh, yeah, hell yeah. That is a probability. What's the largest it could be? 1. So yeah, if you get anything bigger than 1, or anything negative, I don't know how you get a negative, but if you get anything bigger than 1, something went wrong. Something went horribly wrong. Yeah.
For this one, would we have to put it in a percentage?
You could, you don't have to. So I'm hoping that using the z-score chart, you're getting used to seeing probabilities as 4-digit decimal numbers. You can change those into percentages if you want to. That's a human invention. You can change it into a decimal, into a percentage. That doesn't make it wrong, but you don't have to. Yeah. I like it. I like when he's saying that's a human convention. You humans and your weird shit you do. All right. I'm letting too much. All right. Okay, cool. All right, so how about any questions from homework stuff from chapter 6 before we get back into chapter 7? Believe it or not, we are in 7. Or have I completely squeezed any hope and joy out of you? Remember, you can make corrections to quizzes, right? Each quiz counts for maybe 4% in most of your grades. So even if you completely bomb this quiz, it won't kill you, right? Just make corrections and do better on the test. Yeah. Of course, you always have until the day of the next test to make corrections. And when is the next test? Holy shit! So I have the practice test today. So I'm going to give you this quiz back on Monday, and then you have an entire 2 days to correct it. Yeah, I know. Be careful what you do with it. All right, cool. So anything left over from chapter 6 homework? Man, you guys look so despondent. I should be used to that by now. Taught math for so long. That's what I do. It's part of my function. Give me your not despondent and I will make you so. Okay. I'll stop making stupid jokes for the moment. We're going to get back into chapter 7. And just to remind you guys, we actually went to 7.3. So what I'm going to do is, I'm going to finish talking about the basic thing in 7.3. We're going to talk about 7.2's version of it. And then we're going to go back to 7.3 and firm it up, because 7.3 introduces a brand new idea. All right, so that's the pattern of today. So let's kind of remind ourselves where we left off last time. So this is from 7.3 again. We haven't talked about 7.2 yet. The formula for a confidence interval. Confidence interval. Yeah, so it's an interval related to a certain percentage confidence that you want to have. All right, so how far out from the mean that you found do you have to go to be so confident that it catches the real mean? All right, so let's start with concrete. Let's start with a concrete problem to see what the hell is going on with this. And don't forget, remember, this comes from an old formula. This comes from mu plus or minus z sigma. All right, the plus or minus is really just because I'm going up and down. I'm going so much away from the mean. So it's really coming from this little formula here, where z could be positive or negative. So I mean, it's an old formula, but I normally don't know the mean, so I have to take a sample and calculate the sample mean. But the minute I take a sample mean, and I'm talking about sample means, I have to change the standard deviation, right? I really want you to see, it's not a new formula. It's just that I have to replace the parts with what I'm using at the moment. Okay, at all with me. All right. So let's do a concrete problem. Let's see if you guys can get this. A lot of stats is heavy concept, and then it's just plug and chug stuff. But the concept, the more you understand it, the more you know when to use which formula. right? So let's say we have this. Let's say we take a sample of 48 cars. We'll find the mean miles per gallon to be X bar equal to 25.1. We know sigma is, what do you want to say, Jeff? Say it, 3.87 miles per gallon. So we take a sample of 48 cars because you want to see kind of like what the gas mileage is. So it's just 48 randomly selected cars, right? Not SUVs, just cars. We find a mean per gallon, a mean miles per gallon to be this. We know that the standard deviation of the population is this. That's not something that doesn't happen. We sometimes will know what the standard deviation of a population is. Like the last time we talked about the dolphins in the lagoon. I kind of like that one. That was kind of nice. Where they're dolphins, so they have to still follow what the population standard deviation of all dolphins is. But there are specific population that have their own mean. So I can find a sample mean, but I can use a population standard deviation at the same time. You guys semi with me? You guys with me? 9%. Shit. Over 0%? Yes, over 0%. Yes, all right. I'm going to get a shirt. We are with you over 0%. Okay, good. All right. So this is old news. We've seen statements like this. We've done work like this. This is fine. We're just going to use it in a slightly different way. So let's say, I want to create the 90% confidence interval for the true mean gas mileage. We'll just say gas mileage. We'll just say MPG squared for cars. So this is, I would put money on this being not correct. And I'm a teacher, I don't make a lot of money, but I would actually bet a decent amount of money this is not right. Because it's just from a sample of 48 cars. You with me? Understood? Okay. So what I want to do now, the whole idea of this is to take my best guess for what the mean is and go out far enough that I catch, in this case, 90% of the data. So this confidence interval we're about to create, I'm going to go from 25.1, and I'm going to go up and down so many standard deviations so that I catch 90% of the data. So that would mean I am 90% certain that this confidence interval catches the real mean. Why does it make sense? How much data do I catch? I catch 90%. So what's the probability that the mean is in there? There's a 90% chance, right? You guys with me so far? I mean, I don't know if you're just waiting for that, when is he going to lower the boom? Because it's hard for me to tell. It's just difficult for you so far. I mean, this is, the idea sometimes to me, I think, is almost too easy, and you guys don't trust it. You're like, when is the weird shit going to happen? Or you're saying, this is the weird shit. I can't tell. I can't tell with you guys anymore. To me, I think it's almost too easy to believe that I take a sample mean. That's my best guess for the middle. Now, if I go up and down enough to catch 90% of the data, then I'm 90% certain that this will catch the real mean. So then I can say I'm 90% certain that the interval from this to this has the real mean in it. It kind of gives me an interval of where the real mean should be, which is good to know. Yes? Oh, good. All right. So we have, what's the population in this case? No, that's the sample. What's the population? Replace the number with the word all. All cars. 48 is the sample. That's where we got X bar from, right? I'm trying to say something about all cars. So all cars, if I took all cars, do you have time for that? Do you have time for that? Okay, neither do I. But if I did, I would find the real mean. This is what I mean by the true mean. This is the true mean. That's why we give it a Greek letter, right? It sounds like a weird fantasy movie, I know. We must find the true mean. My false mean. Right? So this is the false mean, but it should be close to the real mean. Right? Some weird Monty Python Holy Grail thing going on.
So you're saying the population is the X bar?
No, definitely not, because I know X bar represents a sample mean, and why is X bar? Because it came from a sample. Cool. But what's the point of statistics? Take a sample and try to say something about the whole population. This is what's called inferential statistics. This is not just descriptive. I'm going beyond analyze. This is done. The analysis is done here. Now I'm going further. Now I'm saying, can I infer something about the entire population? Okay. So I'm trying to say something about this, which I think we all agreed none of us could get. None of us have the time. We can go look at 48 cars. Sure, I got time for that. And I can see what the miles per gallon is. Get a mean. But now I want to use that to say, where does it look like the real mean is? The mean of the population. All right, here we go. So what do I know already that this formula needs? What parts of the formula do I already have? Yeah, I got X bar. Check. I got standard deviation. Check. I got N. Check. What's the little holdout? Z. What's your problem, Z? So how do I find Z? Where does it come from? From the 90%. Right? How do I got to figure out how far I've got to go out to get 90% of the data. Now, why do I know Z scores correspond to percentages? Why do I know this is normal enough? Beautiful, the sample size is more than 30. So since n equals 48 is bigger than 30, central limit theorem says good to go. All right, so help me out. Can you guys, so now we know it's normal enough. So can you go ahead and draw a little normal distribution? Draw a little normal distribution. Sure. Sound effect or not. Where would my best guess for the mean have to go? Where am I going to put it? In the middle. So when we get to chapter 8, we will talk about, and let me go ahead and talk about it right now, that is sort of a failing of confidence intervals. They're decent for getting a feel for where the real mean might be. But their main failure is, that's not the real mean, but it's my best guess. The book calls this a point estimate. Best guess, right? What's the best guess for the mean? Well, the mean that I got. That's my best guess. You guys with me? If I truly randomly picked 48 cars, that mean should be close to the real mean, shouldn't it? That's the whole idea of random. It should represent the population. It should be close. All right. So how do I find the z-score then? I want to go out so far that I catch how much?
90%.
How do I find the z-scores here then? Yeah, how much is going to be on this side? Beautiful. If there's 90% in there, there's 10% outside, there must be 5% down there. And you look at your z-score chart and tell me what that is down there. Once I get one, I got both, right? And this minus plus is in the formula. That's the minus plus in the formula there. That's where it relates to, right? So what do you guys get for the z-score? This should be the asterisk dude. This should be the asterisk dude, right?
So for positive Z, would it be positive 1.645 or still negative?
No, yeah, it's definitely positive 1.645, yeah. Yeah. In fact, just to make sure you understand, if I wanted to find this z-score from the beginning, how much is below it total? 95. So if you look at 0.95, you'll get positive 1.645. But why do that? Because of symmetry, I just need one. And the negative one's the easiest to get. And the other one's just going to be the positive. Let me stop there for a second. All right, so enough stuff. All right. Let's see where I got some room here. I got no room anywhere. Scheisse. All right, you're gonna go away. All right, so let's do. What do we got here? We got x bar is 25.1. Z we know now is 1.645. Please don't freak yourself out. I know there's two of them, but the value of Z is 1.645. The plus or minus is built in to the formula, right? Don't try to put plus or minus, and you're like, plus or minus? No, stop. So sigma was 3.87, and N is 48, so now it's just a plug and chug situation. Right? So I get 25.1, give or take, this many standard deviations. Let's take this away now. Be really careful. Don't change the standard deviation by dividing by square root of n and then put it over the square root of n again. You guys see what I'm saying? Don't divide it by square root of 48 twice. That's crazy. Either do it in the formula or do it by itself. Don't do it twice. So what did I call this piece? What was that piece? That's this give or take that. That's the error. That's how much I think I'm off by, right? If you say, how old do you think I am? And you're like, I think you're like 38, give or take 7 years or whatever. That give or take is how uncertain you are. Do you understand? That's beautiful. That's why we call this a confidence interval. It relates to how confident, how certain we are with what we're saying. That's exactly what we do in real life. Give or take that. When can you have it done? We can have a car finished in a couple hours, give or take an hour. Right? When are you going to be here, cable guy? About 6 o'clock, give or take 7 hours. So the first thing I would do is to figure out what this error is. What is that when you plug it in the calculator? So I get this here. Is that what you guys get? All right, and now you just got to subtract this from it and add this to it. What I do is let me show you real quick, and then you never have to do this. See this little button right there? See the little stow button? Store it in X, and then I can do 25.1 minus X, and 25.1 plus X. So I get, this is 24.18 up to 26.02. Right? And that looks like an interval from algebra. Remember interval notation with the brackets and the parentheses and shit? Remember those? Don't freak out. We're not going to suddenly do a bunch of that. But that's why it's called interval. It's an interval. Now, here's the best part. Here's the best part. You have to write a paragraph at the end. Not a paragraph, a long sentence. And I'll grade you on grammar. No, I won't. That's what the April thing. I had a math teacher that graded us on grammar, and we're like, shut up. Not that grammar isn't important. It is. So here I can say we are, how confident are we? We are 90% confident. Because we made a 90% confidence interval. We're 90% confident that the interval 24.18 miles per gallon to 26.02 miles per gallon contains the true mean mile per gallon for cars. So then if somebody said, do you think that the miles per gallon for cars is like 22, what would you say? Do you think it's 22 miles a gallon for cars? What do you say, based on what we've done? You say, no, I don't think so. What's the probability you're wrong? 10%. So if you wanted to be more correct, more accurate, you would create a stronger confidence interval, which means you'd create like a 95% or 98% confidence interval, right? How you guys doing so far? So the only thing you won't be given in the problem is the z-score, and the z-score comes from the confidence interval. It comes from how confident you want to be. It tells you how far out you got to go. So if I want to be more sure, I always used to teach this with I don't fish, but I used to teach you like casting out a fishing net. And there's a certain fish I wanted, and then I wanted to be more certain that I caught that fish, I would cast out a bigger freaking net, right? So this is this big, all right, bam. If I want to be more sure that I catch the damn thing, I'm going to make a bigger net. I'm going to make this go slower and make this go higher. And how would I do that? I would make that number bigger. And what would make that number bigger is make the confidence go to 95 or something higher than 90. That would push it out. Maybe. I don't like fishing either, but it's still a good analogy. You all know what I mean when I say fishing net. All right. I'm going to make that assumption. Okay, so here's kind of like the next level, and then I've got a little handout for you guys to work on. Everybody got this here? Okay. Analyze this error for a second. You can imagine. Oh, I shouldn't have braced all the shit we just had. I'll ask you for it here in a second. So in the problem we just did, the error was for n equal 48. The error was what again? I almost remember. What was the error we got?
0.92.
Oh, thank you. Yeah, 0.92. Yeah. Thank you. You're like, it's right there. All right. So let's say that that's not good enough. I don't want to be that far off. I want to be within 0.5 miles per gallon. You see how that's within 0.9. So if I tell you, can you guess my age to within 3 years? That means I'm letting you be too high or too low by 3, right? So that give or take, the error is the within. So that within is a magic word. When they say within, that's the error. So if I want to be within 0.5, which means now I know what the error is. And I want to say, well, how large of a sample do I need to take to do this? And why does it make sense? If I take a larger sample, what should be true about the sample mean I get? It should be more accurate, which means my error should be smaller. So the quickest way to make my error smaller is to take a larger sample. So this is a feasibility study. Oh shit. Are we cool with the word feasible? Is it feasible? Is it possible? Is it practical? So it's a feasibility. If I have to take another like 50 cars, that's feasible to get within 0.5. But if it takes another 5,000 cars, maybe I don't need that. Sour grapes. I don't really need that. That's fine. You guys understand? So this would be a finding a sample size problem. So watch this. You understand what I mean when I say this? The error is that. Right. So you better, because I've been saying that already. Right. So now it's just written more like a formula. Can you solve that for n? Here's your next little bit of algebra sneaking in. Can you solve that for n without going insane? I like that. And somebody's like, that's an easy question, Jen. No. I've got that one right. The quickest thing you can do first is, I don't know if you remember, I think I talked about this before. Boop. You multiply that up, you divide that down. So they just switch places. And let you absorb that for a second. That's a really cool algebraic manipulation to know. These just switch. I can multiply that up and divide that down so they end up switching. All right, that was amazing. And then how do I get n? Square both sides to kill the square root. So I get n equals z sigma over e squared. So let's figure this out. How large of a sample? 48 sample size got me to within 0.92. Now I'm saying, how large does my sample be to get it to within 0.5? Half a mile a gallon. I want to be within 0.5. So remember, what was our z? Our z was the 1.645. What was our sigma? 3.87. Cool. So now we got everything we need for that formula, right? So the z was 1.645. The standard deviation was 3.87. And what's the error that I want? 0.5. I want to be within 0.5. That's the error that I want. If I put 0.92 here, the answer would be 48. Because they go together, right? So most often people put that there because that's the only error they see. That doesn't make any sense. I want some better error. I want to be closer. So let's see what you get when you do that. So that's what it could look like when you put it in. You only need as many parentheses as I have up there. So I get that. What do you think you should do with this? Can you get 162.114 blah 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 cars? If you can, I'm worried about that last car you got. Right. You have to have at least that. So what do you think you should do with that to make it more real world? You got to go up always. I don't care if that's not round. You don't make it 162 because then that's not enough. It's got to be at least this. So we go, okay, 163 for the real world. Thank you. So how many more cars would we need to find? I've already got 48, right? I've already got that data. That data is still valid. How many more cars do I need? Yeah, 115. I've already looked at 48 cars, right? So I just need 115 more. So that's feasible. We could do that. If it came out to 5,000, we might go, okay, maybe let's reel back on this. Let's be okay with being off a little more. Maybe. Yes, ma'am.
So 115 is your new end, right?
115 is the additional cars. So at the end, my N will be 163. Because I got this 48 already on my list. Now I just go and add 115 more. So overall, I have 163. Does that make sense? Does that make something resembling sense? Is that? Huh?
Can you say that one more time?
Does that make sense? Oh, you only have. What did I just say? Oh, I have to have a total of 163 cars to be within 0.5 miles a gallon. I've already got 48 cars that I looked at, so I only have to look at 115 more to have 163 total. Right? Good. That's all it's saying. All right. Yes. Which part is confusing?
Like, I don't know, the whole thing. You like did it really fast, and I'm just like, really.
Why are you doing this in 48?
So how many total do I need to be within 0.5 miles a gallon? How many total do I need? 163. I already have some cars I looked at, right? I already looked at 48 cars. So how many more do I need? 115. So on the test, I'm not going to take points off if you don't. I'm going to say how many more would you need. If you just stop at 163, I'm going to put a little note. I'm not going to get points off necessarily. In the real world, you wouldn't do more than you have to, right? You're going to go, well, you already got some of this shit done. I only need that many more. Yeah.
So then with 115, would you have to redo everything with 115 as your end? Or what do you do after
You
that?
could, but you wouldn't have to, really. You take 115 more, you get that sample, and then you know from this work that it should be within half a mile a gallon. Right? You kind of with me? You could redo the work, but it would come out to be this error.
Okay.
That's what this work really did. You wouldn't have to redo it. You already kind of know that's the error that you're going to have. Because you forced it to be this.
What's the point of doing all this? Is just to find 115?
Yeah, because if you're trying to put a machine together and it needs a certain size screw, but it's just such a specific size, you're worried that you can't always make it that size. Like just the machine you're using, it could be a little bit off. So you want to. That's not quite the right example I want to do. Shoot, let me think. So if you want to write an article and you want to say that between this and this many people will, let me see, if you eat this certain food, your chances of getting cancer will go down by between this and this much. But if you say that your chances of getting cancer will go down by between 0 and 48%, do you understand how that's shit, right? So your people will say, our error needs to be really fine-tuned. How many more people would we have to go talk to or analyze, or how many more case studies do I have to go take a look at of people who've eaten this stuff versus who haven't, to kind of narrow that error down? So we pick an error that we want it to be, that would be good, and then we say, well, what would it take? So if it only takes like a little bit more, okay, but if it takes like thousands more, I might go, maybe we won't write this article yet. Good, all right, thank God.
Making a new population, or a new sample, basically?
Is figuring out how large. We stopped at 48 because we didn't know shit. And we did it, and we got to within 0.92. And then our boss says, no, I need to be within 0.5. We're like, oh, shit. How many more cars would we actually have to go do? 115 is not horrible. We've already done 48. That shouldn't kill us, right? But if that would have been 20,000, I might go, this job ain't worth that. Sorry, boss. I got to go, right? That's why it's called a feasibility study. How feasible would it be to do this? Okay, so let me give you this.